A little bit about who I am real quick. I'm a technology strategist focused on emergent technology. I'm also an enterprise architect with about 25 experience now overall in emerging technologies. I've been driving the emerging technology wave since punch cards were the thing to do. So it's been a fantastic ride. I'm really happy about that. Some of the organizations I've been with on here, and some of my links on the web in case you need to find me. I was fortunate enough to be enterprise architect at Dell when Paul founded ISA and helped launch the organization a little bit many years ago. Was Austin chapter president for a couple of years there as well. So I'm really happy to be able to contribute back a little bit here today. Let me see here. So here's my objectives for this talk. As technologists, or technophiles at least, it's really easy for us to dive to the gory details, as it were, and lose sight or miss the opportunity here. You know, this machine learning is not just all the bits and pieces that go into it. It is a sea change of the way we're attacking some of our most complex problems, and my focus here really is to try and provide a high-level perspective on things rather than a technology deep dive. If you're not deep in machine learning, I hope to explain why it's critical now and some useful resources to get going on it. If you are a machine learning expert, I hope I can give you some of that business insight that allows you to back off and sell this to your organizational leadership on why it's important. Sometimes it's really easy to talk about all the details and again miss why machine learning itself is significant for us. Let me start with a couple definitions, 3 here: artificial intelligence, machine learning, and big data. And the reason I'm trying to do this is sometimes they become commingled. Artificial intelligence, that term has been around for decades. It is an overloaded term, a superset, makes a lot of promises, raises a lot of concerns and fears. Basically, artificial intelligence was perceived around this notion of neural networks back in the late 50s. All of machine learning fits into artificial intelligence, so that's a superset term. But what I want to focus on for this talk is specifically on machine learning. Okay, I think they joke about artificial intelligence. We've had even leaders like Stephen Hawking, Elon Musk come out recently and say they're afraid of emergent machine sentience that could be an existential risk for humanity. I'm not going to address that. I'm not going to talk about that. I'm talking about something that's much more close to a function that we can leverage for a specific purpose. Machine learning itself is defined by algorithms that learn from data. Okay, they teach themselves or provide some level of supervised training, but essentially we're really talking about callable functions that get better over time because they have learned patterns and sussed out information in the underlying data that may not be apparent to humans. Okay. Some of the concerns about machine learning are, if you consider perhaps one way to look at machine learning mathematically is trying to determine given a current data set, if you draw a curve through the data set, what is the underlying, excuse me, mathematical function that defines that data set or might be underlying the distribution of data. There are a couple areas of error with machine learning. You can overfit a curve. In other words, you might go to try and fit a curve around statistical outliers and determine rules that aren't really there, or you might underfit a curve, in which case you may miss significant pieces of what's underlying the data, the logic. Another challenge with machine learning is it's sort of black box logic. You've got inputs and outputs, but for the most part there's no such thing as like an explain plan for databases. There's no looking at the underlying logic and finding out how the machine learning came to that solution. There are some analytics in this case, but in a lot of cases it's kind of black box to us, and people have concerns over turning control over to mysterious functions. They don't know how they operate. Big data is also an intermingled term. With data, big data, we're really trying to get after data insights to move from data to information to knowledge about the data set and ultimately wisdom. Big data is often not done real time. The differentiation between machine learning and big data that we're looking for is machine learning is more about taking action, and big data is more about deeper understanding. Okay. I will continue on here. So the promise of machine intelligence has been around for almost 50 years. The original models for neural networks were laid out based on neurologist understanding of neurons in the brain in the 1950s. We had a mathematical model that was implemented as a hardware thing, the perceptron, a single neuron, in 1958. And, you know, science fiction has been promising this for a long time. The scientists have been working on it. I've said it's just around the corner for a long time as well, and it just has never materialized in any significant way. But things are happening now, and there's a reason that things are happening now. In one aspect, the precepts of modeling a neuron or a neural network for machine learning has not changed so significantly since some of those initial efforts. What's happening mostly is that compute and data has caught up. Okay, so a lot of the things that were theorized 2 or 3 decades ago are actually coming to fruition because we actually have the compute power to do these things. Let's walk through this just a little bit. Let's see, 1950 we have some of the early inceptions. Adeline in 1960 was a first neural network. What they determined was it's mathematically impossible for a single neuron or neural node to do a simple like an operation like XOR alone. Standing alone, a neuron is not very useful. It is when they are networked in tiers into networks that they become powerful. So the output of some neurons becomes the input of others. Through the 70s, they had what they call the AI winter. Basically, there was a lot of disillusionment, loss of functions, the promises that were there. We go through hype cycles. That happens all the time. In the 1980s, they worked on something called backpropagation. It was initially an issue, but it was something they learned how to leverage in the functionality as well. 1990s, we got a little more interesting in terms of the different algorithms, support vector machines. I'll tell you one thing that's really people overlook often machine learning is it's games like Quake and Doom that are causal for the inception of the capabilities we have now. Is the advent of PC class GPUs that are you know, massively parallel in capability that give us some of the platform that we can actually compute machine learning on. Also in the 90s, we ran up against CPU speed limits. You couldn't go faster and faster, megahertz or gigahertz. We had to go to multi-core processors. Again, computation shifting to parallelism was causal for some of the capabilities that allow machine learning as well. We have some papers coming out in 2001 about unsupervised machine learning as well. And the programmable GPUs were very important too. You see here the NVIDIA GeForce 3 in 2001 as well. In 2006, they started mapping. This is Stephen Ewan, and again, I think it was mentioned Andrew Ng. some other folks started mapping these neural networks to GPUs and allowed to use the massive parallel capability in those. Cheap. Coming into this decade, we have concepts like deep learning, and we're getting some more output, okay? If we did a curve from left to right along this graph, you have exponential capability going up. If, 1950s, we have a functional, slow, single neuron, now we're getting to places where we have widespread real-time language translation, image recognition, self-driving cars, all sorts of capability that's coming out. So what happened was, basically, we had cheap parallel processing meeting these vast data sets. Think of Google, okay, all the data in the world collected in one place and analyzed. That becomes a training set for these networks. And, of course, the improved algorithms. With the deep learning allowed us to overcome some of the backward propagation issues that we had in the past as well. A little look at neural networks. Thankfully, Matt and Bhagwan covered this in greater detail. It's easy to imagine individual nodes as neurons in this. Think of them as mathematical operators with thresholds. From a compute perspective, think of them as analog circuits, right? They get up to a certain point and then they flip over based on the various inputs. In this 4-layer neural net, we have 4 inputs on the left. The outputs of that become the inputs in the next layer, become the inputs in the next layer, and then you finally see the output. So these, you can take, for instance, a 4-pixel image and resolve it to yes or no about it being a certain color or that sort of thing. Taking much larger scale, you can do image recognition in this way. One of the challenges with neural networks is those hidden nodes are invisible for the most part. And as you get errors within those, you get this back propagation, which can be an issue. Okay. We'll go to the next slide. So how do you train these neural networks? You've got these complex systems, but they really need to learn to do things. And there are 3, maybe 4 learning methodologies of reinforcement learning that's not shown on this. It's sort of a variation on supervised learning. But there's 3 different modes here, and I think Bhagwan had a illustration on his title slide showing one of these methodologies, but let's start with supervised. So supervised learning is typically used for classification or regression. The input data, we all know what it is, okay? This is a picture of a cat, and we have it labeled with, desired result, cat or dog type of thing. We do a prepared model for to train the process. It has to output a result, the machine learning mathematical model, as it were. And as we feed the data in, the result comes out, and if the output is incorrect, then we correct it because we know what the original source is. So if it says dog and we want cat, we tell it no, that's a dog, or no, that's a cat. And this can be done iteratively until the results improve. And what you're essentially doing is, if that neural network is a set of nodes that each has different thresholds, think of them like adjusting potentiometers in an electric circuit or something like that. We're trying to balance out that network and the algorithm so that it actually produces the desired results based on the training data. Okay. A couple different algorithms we use for supervised training. Unsupervised training has been a more recent and very powerful development. It's used for clustering, dimensional reduction, association. We use it when the data is not known. Unsupervised learning is often used for clustering analysis. So maybe recommendation engines might say, okay, these 4 book titles often appear close together. if you read this one, you might like that one. Or it might be using for determining or identifying outliers, which is a key functionality for things like fraud prevention. Okay. In unsupervised learning, we don't know what the data is. We just, here's a stack of pictures. We don't know if they're dogs or cats. We do some preparation with the model by deducing general structures in the data, and the output is simply the output, and sometimes there's not a regression testing. The challenge with unsupervised learning is it is somewhat blind, the output. There's not an opportunity really to improve the output, and some people don't like the lack of human training in this case, which brings us to semi-supervised, which is kind of a combination of unsupervised and supervised as a learning methodology. So we've put in the data set. We have some parts of the data that are classified dog or cat, some of it's unknown. Again, we can use it for clustering, classification, regression. We put the data into the algorithm of the output data that we know the correct value. If it's incorrect, we correct that and train the algorithm. The underlying algorithms are used are extensions to some of these other ones, logistic regression, a priority, that sort of thing. In that particular, that's sort of a marriage of supervised and unsupervised. It allows us to do a training that has some human input on huge, massive data sets, and allows the algorithm itself to decipher what the similarities are between the unknown and the known. And we have systems like this are capable, have been last year exceeded human image recognition capability. So better than human recognition of photographs for the identification are capable through some of these types of systems. Anyway, I'm just trying to do a survey there of the high-level stuff. Deep learning is another term that's come around lately. To be honest, deep learning was initially proposed as a rebranding of AI to escape some of the stigma that it had for decades of failing to deliver some of its promises. What deep learning really is on the covers is an update to the old neural networks schema. It takes advantage of modern computing capabilities such as abundant parallel processing, huge data sets, that sort of thing. It allows us to build more complex, deeper neural networks, and it overcomes some of the back propagation challenges that were hurdles in the early 2000s by sort of smartly pre-populating some of those networks. So we set some of the initial values in the network and use some human intervention to sort of pre-train the thing. There's some algorithms on the right. One of the the sort of the mantras for deep learning is it's the marriage of massive data sets, parallel computation, and scalable smart algorithms. So it's sort of neural networks on steroids, giving us a lot of good results these days. There are many, many other methodologies and algorithms. It would take all day to go through them. For the purposes of this talk, I'm really more focused on how we can get applied, useful, profitable capabilities from machine learning rather than trying to dig into everything and make a computer science lecture out of this. Okay, for the most part, coding of machine learning is most easily done with graphics design tools. Think of these, the first image here in the middle with the kind of the purple boxes as mathematical or algorithmical functions. We have inputs and outputs, and we sort of design a neural network in that, or algorithm in that respect. We then take massive amounts of data and throw that at the algorithm, And again, we can do iterative focus to train the algorithm and tune it up, make sure it's producing the kinds of results or close to the correct results that we wanted. And then we end up with what we could, essentially have a model, which is something that's deployable. In most cases, these are kind of snippets from a couple different platforms. You can develop and train the algorithm, and then deployment is kind of a different challenge. You have a couple different choices. You can do a machine learning specific platform. You can set the thing up as just kind of a RESTful callable function on a platform. Could be anything from a standalone to a cloud platform. Anyway, this is kind of the design. If I'm a developer and what tools I might use, this is the kind of interface we might have. And I've got some other pictures later on. Again, trying to take it out of the hands of, let's see, to make it accessible to mere mortals as opposed to having computer science. So I'm not going to do a survey of all complete machine learning platforms. As I think I've spotted aside in Matt's presentation, you can fill 2 or 3 columns with the names of all the different capabilities and platforms. I'm really looking at just kind of major offerings that are available today that might give you forward, and I do some judicious choosing of what I think might be winners in this space. And really I'm focused here on what are the narrow focus, easiest to use, most likely to win platforms in this case. I'm only covering, I think, 4 of them here. Okay, projecting machine learning winners. As with other things, networked Metcalfe's law applies. Very grossly rephrased, Metcalfe's law says that the value of a network increases geometrically with the number of participants in it. It's why we have an internet. It's why forces like Salesforce, Facebook, Google have become so powerful in the world. It is all of the participants in that ecosystem that makes it strong. Okay. There are a few tech giants today that have good positioning and deep pockets to invest in that space. Given that deep learning in particular and modern machine learning requires huge amounts of data or large data sets, some of these companies are better positioned than others to emerge as a dominant use. There is sort of a virtuous cycle here that the machine learning that gets used most gets trained better, becomes more valuable, gets used most, and so it's likely that some of the big giants we know today will be emergent winners in these platforms. There are many startups. There's been over $70 billion in startups invested in AI machine learning space. Machine learning itself is the lion's share of the AI investment. So since 2010, over $70 billion invested in this space. There's an affinity for cloud implementation, okay? If you have the network bandwidth, the compute at the cloud, the data sets of the cloud, network bandwidth continues to improve. We don't have to push this down to the edge in many cases, although we see several things like chips in phones and cameras doing obviously machine learning capabilities like facial recognition, smile recognition, those kinds of things. But for the most part, keeping stuff in the cloud allows the algorithms to get smarter, allows the compute of capability there, and allows continued training. There's here's an analogy. Years ago, when Sergey Brin was asked about Google's search engine, his thought was, we're really building an AI. When you go and do something like search for Santa Claus in Google Images, and it presents you a page of results there, you may pick on the image you want first or second, or you're going to search for one that's suitable for you. Not only is it giving you valuable information or output from the service, but you are in fact also training Google's machine learning algorithms. You're training it what the best or most acceptable with your click, though you're voting for the best Santa Claus picture or most accurate representation of that. So the engines that do these other activities also train the machine learning algorithms, and this is this virtuous cycle I'm talking about. That's how it's hard for a standalone off-cloud contender to actually get the training and the usefulness and capability it needs versus some of these BMOS. Okay, so the key factors on who's going to be the winner: who has the best algorithms, who has the best and largest sets of training data, who has available compute power, and who is used the most. And part of that is open APIs. Open source also enters into this, and ease of use. Some of them remain a bit cryptic in terms of being able to consume the capabilities. So I'm going to start with Google. We've talked about that. It's a decent segue. Okay, some of the core capabilities that behind Google services have been exposed as APIs. So on the right-hand side, we can see their vision, speech, natural language, translation services, prediction. These are all capabilities used behind Google Images, Google Image Search, that sort of thing. Google Translate, of course, the Cloud Translate API. You can do real-time or near real-time language-to-language translation with higher fidelity. And again, it's the same kind of thing when you are correcting the output, you're actually training that service. So what we have here is we have machine learning algorithms packaged as a service. You don't have to know anything underlying about machine learning. You can use that functionality today. We also have capabilities of development tools like Tensorflow, which allows one to do algorithm development training and deployment from a fairly straightforward open source interface. Tensorflow is open source. It's backed by Google. I don't know that there are other implementations of that, but I did catch in one of their presentations that they're using TensorFlow as an input for things like Spark, Apache Spark. So I think it's possible to use that as a tool for other machine learning platforms. In many of these cases, you will find that the capabilities that are surfaced by the platform itself, in this case Google, and the tooling are somewhat coupled together. There's not a write it once, take it anywhere approach in many cases yet. But there's a pretty straightforward approach. These are capabilities you can pick up today and start using. If you need to have translation services for your application, if you need to have speech recognition, image recognition, it's available on tap, and it's all tied together with Google App Engine as well, so you can write applications that use that natively. The Microsoft Azure Platform, I go through a little rebranding this recently. Now it's called the Cortana Intelligence Suite. Again, they have a number of these packaged APIs, including facial recognition, emotion recognition, computer vision, syntactical understanding. This is the picture shown here is a picture of their machine learning studio, where again you're using sort of a function strung together. I keep thinking Visio, where you're developing the algorithm that way, pumping data through it, training it, and later deploying it. It's a pretty straightforward, very friendly compared to the kinds of tools that your computer scientists who develop these capabilities have had in the past. Again, very similar in many ways to Google's offering, where you have the packaged machine learning algorithms that do known functions that are hosted and maintained and improved by the service, along with the ability to create your own and train your own. Okay, and again, you've got some of the same tooling and provider lock-in. So they make it very easy to develop and train algorithms and then deploy it to the Azure cloud, or in Google's case, to the Google cloud, that sort of thing. IBM has things split across two different platforms. They have the IBM Predictive Analytics, which is part of their data grouping of products. Their SPSS modeler is shown here. Again, same kind of syntax where you're designing the algorithm and then training it. This is what's used for developing custom machine learning algorithms. And again, you can deploy these as web services. I think that's it's equivalent both with Microsoft and Google as well. They have RESTful APIs, so you can just use them as a web service. They also have the Watson Developer Cloud hosted on their Bluemix PaaS. They have strong SDKs in there, but it doesn't appear that they have actual machine learning algorithm development as part of Watson Developer Cloud. They do have packaged services that are useful. And again, speech input and output, vision, language recognition in terms of language translation. The trade-off analytics is a Watson-specific capability based on this Alchemy acquisition they had, and basically it allows to balancing of multiple goal sets. So you want to maximize profit while also optimizing delivery time for a customer. It can, for a logistics operation, it can help suss through that and have these goal setting the algorithms and do the trade-off analysis. Alchemy Data is a social network and blog tracking type thing, so you can have essentially all the world's blogs indexed and capable search sort of immediately. So it is sort of a very optimized search engine. It's one of the ways to say that. They also have weather prediction as a capability as well in that. There may be other capabilities in IBM's platform that I'm not aware of, but this is what I was able to find out. I have not used their platform in particular. Amazon Machine Learning is Amazon Web Service, AWS hosted and integrated. It seems a little bit rough. Everything is a web interface for this. There's not necessarily the visual design capability of the tooling. It does give you nice graphical output. The thing is wholly hosted. You never have to learn about any of the underlying nastiness. It really is talking about taking algorithms. It uses more of a data table or spreadsheet functoid type approach than the graphical approach that other tools use. It's got some good outputs. It does not, as far as I can tell, have packaged services. So vision, image recognition, or speech recognition is a capability, although certainly they have that through their Alexa platform. Anyway, in my view, again, I haven't used it. It seems a bit rough and nascent. There's some good cases. Probably also worth honorable mention here is Facebook's offerings, Facebook Learner, and the Face API. They can do facial recognition, syntactic recognition, so it understands the intent and meaning of conversations, those types of things. Anyway, that's a very rough view of some of the platforms, and those are the ones that I think are probably going to prevail in terms of their cloud-hosted and their near large data sets, heavy investments by the different organizations, companies that are putting them together, and a significant amount of expertise, and also some of the capabilities that are driving their success as a company they've exposed as well. Okay, so I've done a little bit into detail, but I want to return to the big opportunity we have here. As technologists, we tend to lose the sight of the forest for the trees. In this case, I think we need to recognize the stampede of sea change that machine learning is, as opposed to the individual tools that are coming out. And I'd like to, basically return the focus to the practical and profitable application of machine learning that you can start doing today. Okay. Why is it important? Just as we went from buggy to mechanical vehicle to computerized vehicles to self-driving cars, the cognification of our world, making everything smart, is a tidal change that is going to transform everything. We can say that practically any function with machine learning will outperform that function alone. And if that's the case, then any function that doesn't have machine learning is going to die, or die off, or be inferior at some future time. My grandfather made his first million by electrifying washing machines, and it wasn't rocket science. Well, maybe it was rocket science in the day, but we took a mechanical thing, applied electric motor to it, go to the bank. Artificial intelligence, of which the bulk of applied investment and capability is machine learning, is today a $15 billion business. By 2020, within 4 years, they expect that to ramp up to $70 billion. This is just one of those curves where the investments is heavy, the output is heavy. Companies are beginning to realize millions of dollars in profit from applied machine learning capability. The machine learning functions like facial, voice, syntax recognition are starting to propagate throughout our world. It's part of our normal daily lives. It just hasn't been applied everywhere. And when it does, it'll be as adventful as perhaps web or social computing or cloud computing. Okay. Here's a quick slide on some of the acquisitions up to a couple months ago. We're missing a few most recent ones, but you can see who's buying what. Okay, Google's buying a lot of stuff. We also have Twitter, IBM, AOL, Salesforce.com, even Apple in this case. These are companies picking up startup companies in the machine learning space over the past few years. Okay, again, $70 billion invested in machine learning startups in some 200 plus companies since 2010. Okay, this is a slide I borrowed from Tata. Basically, it's identifying some of the places that machine learning is being used today in different industries. So, if you think it's only for the technology players or people doing platforms, no, this is the places where we're getting real traction. Actually, one of the big machine learning platforms that's capable of quite a bit is FICO, F-I-C-O, in the creditworthiness evaluation for financial services. They've actually got quite a bit of interesting logic there, and they're capable of exposing that as a platform. Anyway, read through this slide. There are a lot of opportunities. Practically anything you can think of. You know, we're using machine learning and ride-sharing services now to connect A to B and optimize networks and logistics. Obviously, things like self-driving cars and robotics benefit from this. There's a tremendous feedback loop. And it just happens to coincide with the getting data on everything and the whole IoT, Internet of Things push, where we have tremendous quantities of data being produced all over the world. Humans aren't going to be able to analyze and act on all that, but a lot of smart algorithms that can scale can act on that data and can act on that data in timely ways that return value. Okay, so that's a good thing for maybe taking your business. I've gotten through this in record time. Okay, so here's my call to action slide, and basically says, what should you be doing? I'm assuming you are enterprise architects. You're responsible for a portfolio of applications within your company, or you're, hot developers pushing the latest greatest thing, or, basically you're trying to develop something new and bring new business value. Whatever the case, this is what I think that we as architects and business leaders should be doing. One is recognizing that it is likely to be every bit as machine learning is going to be as impactful as SOA, cloud, or social computing trends. There is an urgency to implement not only a business opportunity, but the corollary that if you are the business that does not implement these capabilities, you will be the blockbuster video or the Encyclopedia Britannica of the future. You will be something that used to exist but does not exist now, because you will not remain competitive without this type of capability and insight. Make sure your business understands the important, get it on your roadmap. The last 2 points are sort of classic portfolio rationalization advice. Determine which of your applications give you competitive advantage, adopt there aggressively, look at new opportunities there. What systems you have that are just good enough to keep your company running. Maybe it's your accounting system, your HR system, whatever the case may be. These are not business differentiators for your organization. Then look for platforms or product offerings that, maybe it's a SaaS offering that implements some level of machine learning capability within that. It helps you pick the winners, the emergent winners in those spaces. But basically invest where you get business value and defer or sort of the buy versus build knowledge here as well, where things just come to commodity level. That is the end of my short little presentation here. I've zipped through it in record time, and hopefully it's useful to you. Patrick, are you there to take over?
Sorry, I had myself muted. I was talking to nobody.
Very good.
Gotta love when that happens. All right, well, Brent, thank you so much. That was a great presentation. Really, really informative. I want to open up the floor to any questions we may have for Brent. If you do have a question, feel free to type them into the questions section below, and we will get those answered to you live right away. We do have some questions waiting, so before we get those, I want to start Brent's poll. So if you can take a moment and rate Brent's presentation, with 5 being the best, we would be very greatly appreciative of that. So let's just jump right into these questions. So this may seem like a very basic question, but all of AI seems to be focused on sight and sound, image recognition, speech recognition, etc. Is there any work being done on smell, taste, and touch?
I do know of some systems. There is an artificial nose produced by Johns Hopkins Applied Physics Lab where I used to work. That's probably a decade ago. I don't know that the sensors exist for those yet today with respect to smell. What was the other senses we're looking at?
Let's see, just a second, let me pull it back up. Sight, sound, touch, I believe. Where is it?
Yeah. I think that's largely driven by the sensors that are distributed today. We have cameras, we have microphones, we have touch screens. I don't have a smell-o-vision yet or something that can smell my environment. If the tooling and the sensors continue to propagate, in today's mobile phones, it's not atypical to have barometers, humidity meters, temperature meters, those types of things. Some weather prediction services, for instance, have started using mobile phones as microstations. You sort of filter out the statistical anomalies, but you suddenly have many, many, many more data points, and that's one of the challenges with weather prediction modeling is they're stochastic. The little differences in the starting state can mean big differences down the line in terms of the prediction. And so the more data points we have starting out, the more accurate they can be. So that's an application of machine learning based on instrumentation we have with IoT that might fit in that space.
Great. And the three were actually smell, taste, and touch. But yeah, I think it applies. All right, yeah. Excellent. Moving on, is there any traction in the education industry for machine learning?
Yes, there's some work that's been done on tailored. I have to punt a little bit here. That's not my critical area of focus. When I was with Dell, we did presentations with University of Oklahoma, UT, and some others, and there was great interest in using facial recognition, mood sensing in this case, to determine how engaged particular students were. So think of a MOOC scenario now where you have all of your learners massively distributed, looking at the presentation on their remote computer. The professor no longer has visibility to the classroom. They can't tell if you've lost students or not. We can use facial recognition with some sort of trusted agent that protects the individual user's privacy to determine whether they're engaged, whether they're lost, whether people on this webinar perhaps have drifted off to other things or distracted. That sort of feedback helps us know whether the presentation, the material is effective. We did a demonstration at TEDx in Amsterdam last year that essentially used cameras for mapping the audience, again, their facial recognition, emotion detection, level of engagement for all audience members we could determine that essentially provided the equivalent, if you look at a graph of an audio track of sound, we have sort of an emotional engagement track where people are happy, when they're sad, when they're angry, when they're engaged or bored. We now can go back through. There's a simple website that shows this, but go back through and tell who the effective teachers are. We can find the highlights of each of the presentations by looking at the peak of engagement. So it's a really neat way for us to go through sort of after the fact and use machine learning to develop better content in that respect.
Awesome, awesome. All right. Moving on. Once again, if you have any questions for Brent, just feel free to type them in the question section below and we'll get them answered for you. So can you please provide some of the real-time use cases where machine learning is used widely on the healthcare or insurance
Insurance is around risk analysis. Healthcare is somewhat that, but it's invaded pretty heavily into individualized care. Again, with instrumentation, we can see precursors to health issues long before the patient themselves may see an issue or certainly come to a doctor. I know with what do they call it? I'm sorry. The sort of CDC, when they look at health in large populations, spread of disease, that sort of thing as well. There's been numerous applications in that space, and of course the most obvious one probably is IBM's Watson. They've retasked it to be a healthcare advisor. There was a posting last week about a lady whose life was apparently saved because Watson figured out what was going on with her before the doctors could.
That's pretty incredible.
Yeah.
All right, moving on. How do you do the deployment of trained model through open source technology?
I'm going to defer this one to some of the folks that are deep in the area. We have other presenters that have come through here. In most cases, what I've seen is you have some level of platform lock-in from development to deployment. So if you're going to use Microsoft's Azure tools to do that, you're going to deploy necessarily on their cloud. Same with Amazon. Google, to some respect, even though TensorFlow is open source released, I'm not aware of other implementations of that would allow you to take that artifact and have it portably deployable. So I think other folks that have, one of the presenters sent I'm sorry, I'm bad with names, sent a presentation about using TensorFlow with things like Apache Spark. I think the correct answer probably is stay tuned.
All right.
I do think today there's a bit of tie-in.
Excellent. Before we move on, I want to remind everybody that next month's eSummit will be on organizing architecture, documenting architecture, and it'll be happening September 21st. If you go to the chat section, there is a link where you can click and get registered today, so you don't even have to wait, and you're already set up for next month. And once again, if you have not taken the moment to rate Brent's presentation, if you could do so now with 5 being the best, we would greatly appreciate that. And if anybody has any questions for Brent, feel free to type them into the questions section below, and we will get to those. But moving on, let's go to our next question. How does machine learning fit into the predictive and prescriptive analytics spaces, and could you give us a use case example?
Okay, so for background, predictive versus prescriptive. So analytics traditionally has gone through and said, try to tell us what happened. The next step was predictive, trying to tell us based on data sets what will happen. And prescriptive analytics is basically saying, given a particular goal, try to understand the underlying mechanisms, and prescriptive, prescribe an action that will steer your results toward the desired result. Machine learning sort of does this in small loops. If you think of machine learning versus big data analytics or business intelligence or offhand, I would say, out of loop analytics, what you're looking for from analytics is insights. What you're looking for machine learning is more on a transaction by transaction basis, a smart function. So there's a really kind of an overlap when we get into predictive analytics. If you want to, change something underlying your system based on analytics, are you doing that looking at the data set as a whole, large mass, or are you looking at a specific transactional case versus with an algorithm? The way machine learning works is the algorithm itself is trained to provide specific outputs giving a limited factors of inputs. It does not go back and reanalyze all of the data set for every function call, right? It only looks at the inputs that you would for a normal function and gives you a smart output. Predictive or prescriptive analytics is typically churning against the whole data set, a much larger mass. So I'd say there's some overlap, but the analytics is more intense in sort of learning on the fly, whereas machine learning is proposing a model of functionality. I don't know if that carries across very well.
So how is machine learning architecture different from the ones for big data?
So if you've seen one of the things I was trying to get across with the machine learning as a service, okay, the platforms offered by Microsoft, Google, Amazon, etc., they are making machine learning functions, recognize this face, understand this text, those types of things, or your own role, your own function, machine learning function, available as a RESTful API. So in most cases, I would say do not re-architect your entire application to incorporate machine learning. Determine what functions in your application, what decisions can benefit from machine learning, and develop those functions on these platforms and use them as a web service. That's one of the significant advantages for adoption. You don't have to understand the underlying science, the hosting model, the maintenance, all that kind of stuff. Cloud-based machine learning means that you don't have to redesign everything. Now, there may be folks that take a deeper approach to this and say, no, I need to have the data local and the big deployment and all the other infrastructure there. That's not where I think the rubber meets the road for a good portion of people that want to machine learning enable their applications. I'm advocating a much simpler approach.